Math 1325, we are up to section 6.4 today. This is called implicit differentiation. And the idea behind it is usually you start off with y equals, let's say 3x squared minus 4x plus 5. We usually have functions of x, f of x, functions of x. And f of x, remember, is the same thing as y. So when you find the derivative of f of x, f prime of x, we also write that as y prime. You may remember we called this dy over dx sometimes as well. That means the derivative of y with respect to x. So then you have all x's on this side of the equation. You just do the power rule, 6x minus 4. So everything we've done so far has always been a function of x. And they could have been equal to y or equal to 0 or something else, but they were usually equal to y. And the derivative of y with respect to x is literally dy over dx. And because that was just in the answer slot, we basically ignored it up to this point. What's different now is what happens on number 1. Now we don't have a function of x. It's 3x squared minus 5y squared equals 1. 3x squared minus 5y squared equals 1. So now it's a full equation where there's a mixture of variables. So then either variable could be what they call the independent variable, the one you care about more. But if you're going to do dy, it says find dy over dx. So that means find the derivative of y with respect to x. The denominator one, that's the variable of interest. That's the independent variable. The other variable depends on that is the dependent variable. Well, because before we always had y, we just kind of overlooked this dy over dx for the most part. But it's actually been there all the time. And technically you even get it on the x variable. So what you're doing here is you go to each term and you can see any of the past derivative rules come up. So power rule, product rule, quotient rule, logs, exponentials, and chain rules. Anything from the past can come up. So you go to each term and do whatever's there. This is a power rule right here. The derivative of 3x squared is 6x, just like it was here. But technically you're doing the derivative of x as well. And we always ignored that before because technically what it is dx over dx. The derivative of x with respect to x. But anything divided by itself is 1. So you can think of this just canceling out and equaling 1. And therefore we just ignore it all the time. Because 6x times 1 is 6x. But watch now, when I do this one, 5y squared, you use the power rule and get 10y to the first, but that's multiplied by the derivative of y, which is dy over dx. And then you even go to the other side of the equation, the derivative of 1 is 0. So now, every time there's variables, you need to do the dx over dx or the dy over dx for each of the variables. Although, whatever the variable of interest is, dx, that one you can kind of ignore because it's going to cancel out. So if you're doing equations that are in x and y, then you can just keep doing the x's normally, but when you get to the y parts, you do the appropriate derivative rule, and then you always have to attach a dy over dx to them. And then the goal is going to be solving for dy over dx. If I can get this by itself, I'll have the answer. And I don't care how messy the other side gets. So I currently have 6x minus 10y dy over dx equals 0. And as soon as I get dy over dx by itself with algebra steps, then you're done. So I would just subtract 6x. Cancel this out. Negative 10y times dy over dx. 0 minus negative 6x is minus 6x. And then divide by negative 10y. There it is. dy over dx has been isolated on one side of the equation. Sometimes this side gets real messy with x's and y's. It's okay. And here you could even reduce to, if you want to make that positive 3/5. Negative 6 divided by negative 10 could be positive 3/5. So a simpler version of the answer would be this, 3x over 5y. So the derivative of y with respect to x is 3x over 5y. When that occurs, x is still the variable of interest, the dominant variable, the independent variable. So x is still a variable here. Y is like a constant actually at this point. So it would be like having 3/5 x, but 3 over 5y x, in other words. But you can just, this is just solving it, so you don't need to worry about that. But 3x over 5y. Okay, same thing. Now I have a 6 square root of x plus 6 square root of y equals 5y. So you just kind of go term by term. You might encounter x's or y's. Doesn't matter. But anytime you get one that has y, if it's about x and y, but also the denominator here tells you what the variable of interest is. So x is the variable of interest. Anytime you do an x derivative, then you don't need to attach anything extra to it because it's literally going to be 1. But anytime you do another variable, then you need to have a dy over dx for that part. And I would write these square roots as 1/2 power so we can do the power rule more easily. So 6x to the 1/2 instead of square root of x plus 6y to the 1/2 equals 5y. And we're trying to do dy over dx. Another example of this is when you have different variables, you could do something like, how does the motion of an object change with respect to time? An object is driving down the street, a car is driving down the street, and then over a period of time, what's happening to it? So it could be a change in its position with respect to the time. The time would be the variable of interest. Or in business, how are my profits changing with respect to price? So I could do the derivative of profits with respect to price. If price goes up, usually demand goes down, and if price goes down, demand goes up, so that could affect your profits. So first power rule would be 6 times 1/2. 6 times 1/2 is 3. And then decrease the exponent by 1 to a negative 1/2. And then technically times 1 because you're really multiplying by dx over dx. And then same thing here, 3y to the negative 1/2. But now I have to have dy over dx for that part. And the derivative of 5y, if that was a power rule, you would just get 5 for that, but then times dy over dx. So once you start getting multiple dy over dx's, then you want to move all of them to one side of the equation and all the ones that don't have it to the other side. And I'm just going to leave these as negative exponents for a minute. 3x to the negative 1/2 equals, I'm going to put this first, since it was already over there. And then I'm subtracting this whole term. Since it's currently added, we need to subtract it to move it over to this side. Minus 3y to the 1/2, negative 1/2, dy over dx. And then you're just going to factor out, the greatest common factor is dy over dx. Factor that out. That would leave 5 minus this. And whatever this is, you just divide by it. You don't really care how messy the other side of the equation gets. Divide both sides by that. There's dy over dx by itself. This is probably a good enough answer. Maybe they don't like the negative exponents, but usually in calculus they don't mind that. So I'm going to have, I'm going to put a fraction, 3x to the negative 1/2 for the numerator, 1/2. And the bottom was 5 minus 3y to the negative 1/2. Check that. 3x to the negative 1/2, 5 minus 3y to the negative 1/2. Yeah. So that's it. So you could also simplify those negative exponents. You could turn them back to radicals if you wanted to, but it's a bunch of extra work that doesn't have to be done. We've seen that before in the past too. Okay, so now we got two different x's, two different y's. There's exponents. There's even a log. So now they're just going to hit us with stuff from the past. 2x plus ln of y equals x to the 5th and y to the 6th. Okay, go term by term. The derivative of 2x is literally just 2. And it would be times dx over dx, but that's 1. The derivative of natural log of something, the rule for it is you go 1 over whatever the stuff is. And then with ln, there's a times ln of e, but that equals 1. And then there's also times the derivative of the original stuff, but the derivative of y is 1 normally, except since it's y, the derivative of it is actually dy over dx. Plus, anytime you do a y term here, you should have a dy over dx attached to the end of it. And now I want to do the derivative of this. This is a product. So for this part alone, I got to do the product rule. First, times derivative of the second. The derivative of y to the 6th on its own is 6y to the 5th. But then you're going to need a dy over dx for that part. Plus the second times the derivative of the first, which is 5x to the 4th. So there are 4 terms. There's a 2. There's this with the dy over dx, and there's another one with dy over dx. And then there's a final term that doesn't have dy over dx. So 2 of them have it, 2 of them don't. You just got to move both with it to one side and both without it to the other side. And because each side has 1 of each, it really doesn't matter which side you go to. I'm going to keep this one, and let me move it out a little further out. I'm going to keep this one on this side. And then I'm going to subtract this one over here. And you can clean that up a little and write 6x to the 5th, y to the 5th, dy over dx. And then I can leave this one on this side of the equation, although I'd probably rewrite it 5x to the 4th, y to the 6th. And then move this 2 over to this side, which makes it minus 2. So this term moved there, and this term moved there. The other two stayed where they were. And now I've got the left side has all the dy over dx's, the right side doesn't. And now I can factor out a dy over dx, and this is why I wanted to move this side so it would be on the proper side that we're used to, but it really doesn't matter which side you're on. So then you would have a 1 over y minus a 6x to the 5th, y to the 5th left over. And then you're just going to divide by everything next to the dy over dx. And again, we don't care how messy it looks in the end. Although again, sometimes they don't like fractions inside of fractions, so this fraction right here might be a slight issue, but we'll see if they'll take this answer, and if so, then it's not. But I have seen some textbooks where they frown upon fractions inside of fractions, just like some people don't like negative exponents and answers either. So now it's just a matter of what's your preference for how you want the answer written, because And a lot of these problems, there's multiple ways to write the final answer sometimes. But what I always do, you never know what any particular textbook might find picky or not. So I'm just going to put it in like this, and then if they say it's wrong, then I'll try to adjust for it. So 5x to the fourth, y to the 6 minus 2. And I'll start off with a 1 over y down here in the denominator. Oops. Minus 6x to the fifth, y to the fifth. And they took it that way, so why waste time doing some other extra calculation? But what you could do is you could multiply top and bottom by y. And then when you distribute that here, that would get rid of that fraction. So if you add an extra y right here, add a y right there, and increase this by 1 as well, then you could just have a 1 here instead of 1 over y. But why do all that if you don't have to? Okay, so we're going to still do the same thing at first, but then we're going to do a little bit more after that. So let's do what we did on the first 3 problems first. My equation is the equation of a circle, actually. X squared plus y squared equals 26. X squared plus y squared equals 26. That's the equation of a circle, if you remember that from algebra. So if I do implicit differentiation, that implicit means you're not doing it directly on each variable. That's why it's kind of like indirect instead of direct. So 2x, and that's good on its own. And then this is 2y, but then we need a dy over dx. And the derivative of 26 is 0. So this is kind of like problem number 1, where we just have one term that has dy over dx in it. So isolate that. Two y times dy over dx equals negative 2x. Divide by 2y. The 2's even cancel. So the derivative of y with respect to x is negative x over y. This is how problems 1, 2, and 3 went. In fact, that was very similar to number 1, where I got a 3x over 5y. Okay, so that's the derivative of y with respect to x. Now what they want me to find is find the equation of a tangent line. Tangent line slopes are derivatives. Find the equation of a tangent line at the given point on the following curve. So we have a circle, and then at the coordinate 5, negative 1, and this circle is centered at 0, 0 actually, because there's no numbers in parentheses right here. So at 5, negative 1, maybe like right here, there's a tangent line that would touch that circle once right there. And slope of a tangent line is what derivative's all about. Slope of a tangent line is derivative. I have the equation of a derivative now. And I have a x and y coordinate. So I could plug the x and the y both in. And this would give me the value of the derivative at this one and only one spot. If I move to a different spot, the value of the derivative will be different. But that should make sense, because if you move around this circle, no matter where you go around this circle, the tangent lines are going to be different. That tangent line is different than this one, which would be different than this one. So if you get different coordinates, you're going to have different slopes. And that makes sense, because the tangent line is going to change directions when you move around the circle. So I would get negative 5 over negative 1, the negative out front, the x is just 5, and then the y is negative 1. So that just happens to be a double negative equals 5. So the slope of this line right here is 5 is what that's saying. It's up 5 over 1 over and over again. So the equation of this line is y equals 5x plus something. We don't know the y-intercept. We can kind of tell from my sketch that it's some negative value down here. Maybe like negative 10 or so, just estimating quickly. So, but we can find it by temporarily plugging in the given x and y into this equation now. So if I have -1 equals, the slope was 5, and then the x happened to be 5 as well. I guess my estimate was off quite a bit. It's much farther down than I thought. So subtract 25. It's actually -26, not -10. I was just trying to eyeball it, but it actually makes sense because you're going down 5 over 1, so you're going to be doing a lot of down 5s. -26. So the equation of this tangent line right there is y equals 5x minus 26. It's got a slope of 5 and a y-intercept of -26. And if I moved to any other spot on the circle, it would have a totally different equation of a tangent line, because the slope would be different and the y-intercept would be different. And they already have the y equals ready, so 5x minus 26. Be careful, because sometimes they don't put the y equals, and then if a student doesn't put it, they'll count it wrong. You won't have a full equation is the issue. Same thing, except this is not a circle. X squared times y squared equals 4. Has to be plus to be a circle, not times. X squared times y squared equals 4 at the point -1, 2. So implicit differentiation first. I'm going to do the derivative of this, but that's a product rule. So I have to do first times the derivative of the second, which at first is 2y, but then you need a dy over dx attached to that. What's dy over dx? First times derivative of the second plus the second times the derivative of the first, which is just 2x. And the derivative of 4 is nothing. So there's only one dy over dx, so I just need to isolate that. I would, let's clean this up a little first. 2x squared y dy over dx plus 2xy squared equals 0. So let's subtract this one that does not have the dy over dx to the other side. Two x squared y dy over dx, oops, I didn't write the y, equals -2xy squared. Divide by this stuff here, 2x squared y. There it is. dy over dx equals this fraction. You can even reduce this fraction too. The 2's cancel. I can get rid of this x with one of these two x's, and I can get rid of this y with one of these two y's. So I simplified it down to what looked like problem number 4, except it's backwards. It's -y over x, just by coincidence, I guess. But so this is the derivative equation in terms of both x and y. And I have both an x and a y here. So if I plug them in, I can get the derivative at that one spot. And it's going to work like the last one too. You're going to get a -2 over -1. That'll turn out to be +2. So the derivative at that coordinate is 2. And therefore the slope of the tangent line at that spot is 2. And then we know half of the answer, y equals 2x plus b. And then you can temporarily plug in x and y just to find the b. So 2 equals 2 times -1 plus b. -2. Add 2 to both sides. b equals 4. So the equation of the tangent line, and whatever this looks like, this would be harder to know what this graph looks like actually. That's not even taught in pre-calculus yet. So this, they intentionally give you a graph or an equation that you wouldn't know what the graph looks like actually. So it's all the algebra and the calculus here to be able to do this. The last problem you might have known what a circle looked like to help you out a little bit. But here we've got, what was the slope? 2x, so y equals 2x. And the y-intercept was 4, so 2x plus 4. And they do have the y equals already. 2x plus 4. Okay, just a little bit more stuff here now. 4y to the third plus xy minus y equals 256x to the fourth. And all I'm told is that x is 1. Find the equation of the tangent line, same directions, at the given value of x instead of the given coordinate. So 4y to the third plus xy. 4y to the third plus xy minus y equals 256 x to the fourth. And all we're told is that x equals 1. So let's go term by term. The derivative of 4y to the third is 12y squared. But because it's about y, we have to add a dy over dx. Then xy is a product rule. X times y, you have to do the product rule for that term. So first times the derivative of the second, the derivative of y would normally be just 1. But really what it is 1 times dy over dx. Plus the second times the derivative of the first, which is just 1. So this part alone right there, that just came from this part. And then minus y, the derivative of that is minus dy over dx, because the derivative of y is just 1. And then here we would have to do 256 times 4 for the front constant, 1024 x to the third. Okay, so I have 1, 2, 3 terms that have dy over dx in them. There's technically a 1 right there. And then this is just y right here. So let me move y over there because that doesn't have a dy over dx. And then I can factor out dy over dx off the other 3 terms. So take this away, that would leave this. Take this away, you would just have the positive x there. Take this away, you just have the negative 1. And then you got your 1024 x cubed. And then I'm minusing y to the other side of the equation. Then divide by all this stuff, so you get dy over dx isolated. You're basically doing that part on every problem. Get the dy over dx isolated. You don't care how messy this side gets, at first anyway. There's the equation of the derivative in terms of both x and y. Now, I've got an x to plug in, but unlike the last 2 problems where they gave me an x and a y where I could plug them both in, this one I guess I didn't write it down, but we only have x to plug in. But what we could do is if we plug in, if we were to plug 1 into the original equation, maybe we'd be able to find y ourselves. I think that's what they want us to do, is plug a 1 in here and there, and maybe we can figure out y. So that would be 4y to the third. This would be 1y or just y. Then you'd have this minus y, that's convenient. Those just canceled. And then this would equal 1, so 1 times 256 is 256. Then we could divide both sides by 4, since that's all that's there on that side. 256 divided by 4 is 64. And the cube root of 64 is 4. So I just had to do some algebra to figure out that actually the coordinate we want to plug in is 1, 4. This time they only told you the 1. They didn't tell you the 4. You had to find it yourself. But once you find that yourself, now it's just like the last two problems. Although the derivative is a little more complicated, but now I have this more complicated derivative to plug into, where before it was a simpler one. But everywhere you have an x, put the 1, and everywhere you have a y, put the 4 that we just found. So 1024x cubed, 1024, and I'm going to plug 1 in for x cubed, minus y, so I can put minus 4 since y is 4, 12y squared, so 12 times 4 squared, plus x, put a 1 in for that, and then there's a minus 1. So those can even conveniently cancel, and you won't have to worry about it. 1 to the third power is 1, so the top is 1024 minus 4, or 1020. The bottom is 4 squared times 12. 12 times 16 is 192. Does this divide evenly, maybe? 1020 divided by 192? No. Okay, so then we'll just reduce it. 1020 divided by 192, math, enter, enter, reduces fractions. 85 over 16, at least it simplifies slightly. But we know half the answer now. Half of the answer is y equals 85 over 16, x plus b. And this will be a little more challenging, but at least we're plugging 1 in for x, so that'll just keep this 85 over 16. This will be 4. So I just need to solve 4 equals 85 over 16 plus b. And solve for b. So we need to minus 85 over 16. That's how you'll get b by itself. Just got to get a common denominator over here. So make this 4 over 1 and then multiply by 16 over 16. That way it'll be 64 over 16 for this part. 64 over 16 minus 85 over 16. That's negative 21 over 16. So the final answer is y equals 85 over 16x. We knew that was the slope of the tangent line. And now we know the y-intercept is minus 21 over 16. It's common that if the slope has a weird denominator, that often the y-intercept does too. Although not always. But it did turn out that to be the case here. So 85 over 16x, they already have the y equals. Minus 21 over 16. Okay, here's a graph of 5x squared plus y squared squared equals 169 times x squared minus y squared. This is called a Lemniscate, a figure 8, most people think of it as. And this is also the symbol for infinity, actually. This guy named Bernoulli, he lived a few hundred years ago. He saw this symbol and thought of somebody just forever and ever drawing figure 8s like ice skating. And if you were just traveling on this graph, you would just forever go around and around and around. And yes, that happens on other graphs, like circles go around and around and around. But for some reason, he thought this could be a good representation for infinity, because infinity just goes on and on forever. But then they gave the graph a name. It's called a Lemniscate. We actually study these in pre-calculus. Find the equation of the tangent line at 3, 2. So you can kind of see that here. 3, 2 is right there. So what's the tangent line equation right there? It's clearly got a positive slope to it. And it looks like the y-intercept will be positive as well, but pretty close to 0. Okay, so I just need to do this derivative first, implicit differentiation. We are on number 7. 5x squared plus y squared equals 169 x squared minus y squared. Now you can't distribute this 5, but you could distribute this 169 because there's a square here, but this one doesn't have an exponent. So it might be better if I make the right side 169x squared minus 169y squared. There's no way to simplify the left-hand side. So I need to do the derivative of this all together, and it's really a chain rule. So you want to do the outside first. 2 times 5 is 10 times the base. Decrease the exponent by 1, but then times the derivative of the inside. And the derivative of the inside, here's where the implicit differentiation comes into play. The derivative of x squared is 2x. And the derivative of y squared is 2y, but then also times dy over dx. That's the whole left side. And on the right side, I can just do this term by term. 169 times 2 is 338. So 338x to the first, and then minus 338y to the first, but then dy over dx for that part because it's a y. Okay, now that this is a 1, you could distribute this 10 now. So 10x squared plus 10y squared this one's going to get messier than I thought. And then this stuff's here, but instead of rewriting it, I still have work to do over here. Okay, so we're going to have to FOIL this out, unfortunately. 10x squared times 2x is 20x to the third. And that does not have a dy over dx attached to it. Then 10x squared times 2y would be 20x squared y, and that would have dy over dx attached to it. Then you would get a 20 xy squared that does not have a dy over dx. And then finally a 20 y to the third with a dy over dx equals this 338x and the minus 338y with dy over dx. So there's 6 total terms. 3 of them have dy over dx. 1, 2, 3. 3 of them have it, 3 of them don't. So I'm going to leave these 2 on the left side of the equation. 20x squared y dy over dx plus 20y cubed dy over dx. Then take this negative one right there and add it to the other side. So that'll make it positive 336 y dy over dx. And that way all 3 of those terms have dy over dx in them. Then on the right side, leave this one first, 338x. I say 6 or 8 over here. Yes, I almost had a brain cramp mistake. This should be 8 right here, not 6. So 338x, staying right there. Then this 20x to the third needs to come over here, so minus it. And then minus this 20xy squared over here. Oops, xy squared. Okay, then factor out the dy over dx. which will leave 20 x squared y plus 20 y cubed plus 338y. And there's a lot of 20s here. Okay. Divide by all this stuff right here. I'll just go like that. And then it'll be over here too. 20x squared y plus 20y cubed plus 338y. Luckily, they gave us the full coordinate here because it would be hard to find y just given an x. But they did give me a full coordinate 3, 2 this time. So I know I want to do this at 3, 2. Everywhere there's an x, put a 3. Everywhere there's a y, put a 2. So I need to have 338 times 3 minus 20 times 3 cubed minus 20 times 3 times 2 squared, I think I have there, squared. Looks like a 3, but I think it was this 2 right here. Okay. Then in the bottom, 20, put a 3 in for the x, 3 squared, put a 2 in for the y. Plus 20, put a 2 in for the y. Cubed, plus 338, and put a 2 in for the y. Here's definitely a case for the graphing calculator that can do both the top and the bottom all at once. So I can type in the entire numerator, 338 times 3 minus 20 parenthesis 3 cubed minus 20 times 3 times 2 squared. So I get that all at once, and then the numerator comes out to 234. Now the bottom is 20 parenthesis 3 parenthesis squared parenthesis 2 parenthesis plus 20 parenthesis 2 parenthesis raised to the third plus 338 parenthesis 2. So type the whole denominator in. 1196. So does 234 divided by 1196, type it in as a fraction. Math, enter, enter. It did reduce significantly to 9 over 46. That helps. But certainly not anything anybody would guess. But we now know half the answer. Half of the answer is y equals 9 over 46x plus b. And we just have to plug 2 in for y, 3 in for x, and we can solve for b. So 2 equals 9 over 46 times 3 plus b. When you do a fraction times a number, you just multiply the top. 9 times 3 is 27. And then you can subtract 27 over 46 from each side. I would put this over 1 at first, and then because there's a 46 here, multiply by 46 over 46. 2 times 46 is 92. 92 over 46 minus 27 over 46 is definitely over 46. So 92 minus 27 is 65. So the apparent answer is y equals 9 over 46. Remember I said the slope should be positive, but this is saying it's like a pretty close to horizontal almost. That's close to 0. 9 over 46x plus 65 over 46, which is a little more than 1. So this is definitely a possible answer based on what I was looking at in the picture. Y equals 9 over 46x plus 65 over 46. I don't know that I did this right, but it's at least possible if you look at this graph, because 3, 2 is right there. So a tangent line would go like this. It's getting close to being horizontal. It would be horizontal at about 3.5. So it's a pretty not steep line. So it's getting close to horizontal 0. 9 divided by 46 is like 0.2 or something like that. And then if you extended it out further, it looks like it would cross a little above 1 or 1.5-ish, something like that. So that's definitely a possible answer. Let's see. Yes. Okay. I wasn't sure because these are such weird fractions, but yeah, they're just making this weird on us. Okay, so maybe you could guess this might happen at some point after what we've learned recently. But number 8, we're again going to apply one thing you already know. What if you have 8x squared plus 9y squared equals 10? We could do dy over dx like the first 7 problems. That's the first derivative. But then here's a new symbol, d2y over dx2. It's a little weird how they put the 2 in a different place each time, but here they put it on the d, but down here they put it on the x, strangely. This just means second derivative. That's one symbol for second derivative, besides putting a double apostrophe. If you put 2's that look like exponents, that means you're doing the second derivative. So I just want to do this implicit differentiation twice. And the first round won't be that difficult. Maybe the second round might get harder, or sometimes not, but this will be pretty easy because I don't have any like product rule or quotient rules or anything. So the derivative here is 16x to the first plus 18y to the first, but then dy over dx, and the derivative of 10 is 0. So just isolate the dy over dx first. I put a 1 here, but you didn't need to put a 1. So I'm going to move the 16x over, subtract it. 18y dy over dx equals negative 16x. Divide by 18y. This is very similar to problem 1 and 4 up to this point. There's dy over dx. That's the first derivative. And you could reduce both of these by 2. So the first derivative is negative 8x over 9y. Now do the derivative of that derivative. D squared y over dx squared is a symbol for second derivative. I want to do the derivative of this. Well, this is a quotient. So it's just going to take the quotient rule. Quotient rule is second times the derivative of the first. The derivative of negative 8x is just negative 8. Minus the first times the derivative of the second. The derivative of the second would be 9, but then you need your dy over dx attached to it since it's y. And then all over the second squared. Okay, so I've got a negative 72y right there. Negative 72y. And this double negative could be plus 72x dy over dx. And then in the denominator, you could square this by squaring both parts. Whenever you have a parenthesis squared, you do both parts like that. 9 squared is 81, and y squared is y squared, so I could put 81y squared in the bottom. Now, the only issue is, what about this dy over dx right here? That's probably not going to be part of the answer. But what we could do is, we had an answer for that. It wasn't the final answer, but dy over dx was equal to this fraction. So I could substitute it in for it, and that way I wouldn't have a dy over dx in the middle of the answer. It's usually not good to have, like in a definition, you're not allowed to use the word that you're trying to define in the definition. So I probably shouldn't have a dy over dx in my dy over dx to the second derivative of it. So what would happen if I plugged in right there? What if I just plug in the first derivative answer right there? It's negative 8x over 9y. Well, 72 divided by 9 is 8. You could get rid of that. And then, again, maybe they'll be okay with these fractions inside of fractions. 72y. And then since there's a negative here and a plus here, I could say minus 64x over y, since the 9's gone now. And then this is in the bottom. So in general, we don't care how messy these answers get. There's going to be x's and y's all over the place like this. This certainly could be an answer. And before, they were not bothered by having a fraction inside of a fraction. If they are bothered by that, you can multiply top and bottom by y over y. It's just going to make this y get one larger, this y would get one larger, and then it would cancel that y out. So certainly an equivalent version is negative 72y squared minus 64x over 81y cubed. If you don't like fractions inside of fractions, this would be the equivalent answer. But let's just see if they take that, because then it's less work. So first I'm putting a fraction, negative 72y. Then I need a fraction inside of the fraction, 64x over y. And then the bottom was, whoops, went too far, 81y squared. Okay, so then the next thing I would try is, let me make sure I typed it right first, negative 72y minus 64, oh, I forgot the square is what happened. X times x. This should have been squared, I think, is what I'm missing. I wouldn't think that would cause it to be wrong by having a fraction inside a fraction. When they took that earlier, I just overlooked a second x that I didn't see when I was putting that together. Let's try that. And there it is. Yeah, see, just a brain cramp mistake. I didn't see that I had two x's right here. When I multiplied the 8's together, I forgot about this x down here is what happened after canceling this. So that's the one downside to doing something like this, is you kind of overlook stuff you have written there. But yeah, you can just leave it like that. If I would have written it this way, I'm sure they would have taken this answer too. Some books are real particular about that, and they would count this wrong and force you to do this, but they're definitely more lenient here than other textbooks we've used before. Okay, so let square root of u plus square root of 6v plus 4 equal 3. Find the derivative of du over dv. See, the point here is it's not always x's and y's. So the bottom tells you which variable is really the one of interest. And that's the one where you don't have to worry about anything extra. But the other variable, then you have to do... It's weird, it wasn't going. Okay. Then anytime I do a u variable, I have to attach an extra dv over dv. So number 9, square root of u, or I could write u to the 1/2 plus 6v plus 4 to the 1/2. 1/2 equals 3. And they tell you what they want. They want du over dv. So that tells you which one is the variable of interest. The v is the variable of interest, just like dy over dx. So anytime you do a u variable, you have to attach this to it. That's the chain rule part. So the derivative of u to the 1/2 normally would be 1/2 u to the negative 1/2. Remember, we had one of those earlier. But then since u is not the variable of interest, we do need a du over dv attached to that. And that's the part we'll solve for that eventually. Okay, then the derivative of this is a chain rule. So 1/2 times the base, decrease the exponent by 1, And then the derivative of the inside, since that's linear, the derivative of that's just 6. And that is the variable of interest, so then I don't attach a du over dv to it. And the derivative of 3 is nothing. So let's move this one over. Oh, no, that one's got that one's got du over dv attached to it. So leave this one here. I'll clean this up and move it to the side. So half of 6 is 3. So we could make this a 3 in front. So I'm going to leave 1/2 u to the negative 1/2 du over dv equals, it's positive on this side, so I'd have to minus 3 6v plus 4 to the negative 1/2. And that way I've got stuff with du over dv on one side and the other stuff on the other side. Divide by this, and you'll get the du over dv isolated. Okay, now they might take this answer. I'm guessing they would. Maybe to clean it up a little, here's something that might make it look nicer, because I think since there's part A through C, I think we're going to be plugging numbers into this in a second, and this would be hard to plug into. If you just needed the answer to the derivative, this would be fine. And if you put this in as part A, I think they'll take it. But watch this. I'm going to multiply by the reciprocal of the denominator. If you multiply by 2 over 1 to top and bottom, then this fraction inside of a fraction goes away. And this is just negative 6 right here. U to the negative 1/2 in the bottom can be u to the positive 1/2 in the top. And then this parenthesis to the negative 1/2 can be that parenthesis to the positive 1/2 in the bottom. And then you could change the 1/2s back to radicals like they were originally. I had one of these earlier and I didn't do any of this because all we had to do was find the derivative of it. But now I am doing it because I have a suspicion that they're going to have me plug numbers in. So it's easier to work with these fractional exponents and negative exponents just to find the derivative. But if you have to plug numbers in for v and u, you definitely want to have it in a better format. So square root of 6v plus 4 would be the bottom. So I'm going to plug this into the answer for part 1. Negative 6 square root of u over the square root of 6v plus 4. And then it'll be real easy to plug numbers in for u and v if they need that later. But I'm sure if you plugged in this to the part A just to get that part out of the way, you could. You should be able to plug this in too. That is equivalent to it. But here's a case where doing some extra work's actually going to probably pay off. Or maybe not. Okay. So if they would have given me a u and a v to plug in, it would be real easy. Like say u was 9 and v was, well, it would take a while to figure out what would be a good v, but plug 9 in for u, the square root of 9 is 3. You could do that much more easily than if you had it like this. Plugging 9 in here is hard to do. So maybe I did all that for nothing because now... Okay, so now they want me to start over again from the beginning. And now u is the variable of interest. Here v was the variable of interest. Now u is the variable of interest. So this time I guess I'll just leave it alone this time. Part B. So come down here again. You're starting over again right here. I did take the radicals away at least because that's easier to do derivatives from. U to the 1/2 plus 6v plus 4 to the 1/2 equals 3. I'm going to repeat what we just did, except now v is the variable of interest, not u. Or am I saying that backwards? Oh, I'm saying it backwards. U is the variable of interest, not v. So now u, you don't have to do anything extra to it. 1/2 u to the negative 1/2. That one's done now. Last time I attached a du over dv to it. plus, now here's the chain rule again, 1/2 6v plus 4 to the negative 1/2 times the inside 6, but then times dv over du, since that's the one we care about now. V is not the one we care about, so we need to attach that there. And the derivative of 3 is still 0. So now move this term over there, and 1/2 of 6 is 3. Whoops. Forgot my little dv over du right here. So divide by all this stuff. And this time I'm going to plug it in this messy format. This is supposed to be a 2, even though it looks like a 3. Okay, so let's see if they take this, so that way you'll know whether you need to do this or not. So I got fractions inside of fractions, and I got negative exponents, but let's see if they take that. Negative 1/2 and u to the negative 1/2. And then in the bottom, 3, or was it negative 3? 3, 6v plus 4 to the negative 1/2. Last time I moved the negatives around and put the 1/2s back as radicals. Let's see if they take it in this format. See, they did. So I could have done that for part A too. But that's good. At least you saw it once put back and once not. Okay, so although now it's hard to compare these answers. So if I write this one equivalently, if I had switched this one around, what would have happened is you would have ended up with negative 1/6 for this part. Where can I write this? Negative 1/6. And then this part would go up to the top and be a radical. Square root of 6v plus 4. And then the u would go to the bottom as a radical. This is the cleaned up version of part B that I didn't have to do. And where was the one for A? Right there. Negative 6 square root of u over this square root. Okay, so what do you notice about these two? I guess is what we're asked here in part C. They both have a negative, and then they're basically reciprocals of each other, because this is 1/6 and this is 6 over 1. And then anytime you flip a fraction, that's a reciprocal. And reciprocals have the same sign, so they're both negative. So it turns out they're just reciprocals of each other. Now I don't know what they're saying down here. What did they say here? Based on your results, what do you notice about the relationships? They're reciprocals of each other. Yeah, exactly what I said. I didn't even know they had that there. So that's what ends up happening. They just turn out to be reciprocals. So that could be a shortcut in the future, that if you ever do part A, as soon as you get it, you could just flip it and you would immediately have part B without having to do all the work all over again. This is what we do in math, is we discover something as we work things out, just like out of curiosity. What would somebody was like, I did this problem in terms of V. What if I do it in terms of U? How does that affect the answer? Turned out it was just a reciprocal. Okay, last problem. Here we are in a business setting. We have cost and revenue. X is the number of units sold in hundreds, okay? Find marginal cost. Marginal means derivative. So we want to do the derivative of the cost, dc over dx. That means x is the variable of interest. And then they're giving me an x value of 4 also. So take your cost function and do a derivative of it. C squared equals x squared plus 90 square root of x plus 58. Okay, so the derivative of this, you would do 2c. C is not the variable of interest. We're trying to do dc over dx. That's in essence what they asked us to do. That's the derivative of cost with respect to x. So x is the variable of interest, c is not. Then we need a dc over dx every time we do a c variable. The rest is all about x, so we don't need anything for that extra. The derivative of x squared is 2x. This is x to the 1/2. So 1/2 times 90 is 45, x to the negative 1/2. And the derivative of 58 is nothing. So I've got dc over dx isolated. I just need to divide by 2c. So here's the derivative of c with respect to x right here. But they want me to do it when x is 4. Okay, so I would have to plug 4 into the original equation to figure out what c equals, because I need to plug in for c as well. So they only gave me x equals 4. They didn't tell me what the c or the y value was. Remember that other problem where they just gave us x equals 1. They didn't tell us what y was. So if I plug in 4 squared is 16. Square root of 4 is 2 times 90 and plus 58. What is that? That's 16 plus 90 times 2 is 180 plus 58. So c squared would equal 254. So c would be the square root of 254, which definitely, I don't think that comes out evenly. No. Okay, so we're going to plug in 4 for x. And this is 1 over the square root. So 1 over 4, square root of 4. And then this is going to be square root of 254 right here. This is 2, 1/2 of 45. What kind of answer do they want here? Do not round to the final answer, then round to the 100th. Okay, they do want a decimal. So that's going to work fine in here then. So I can do half of, this is 1/2 right here. Square root of 4 is 2, so that's 1/2. Half of 45 is 22.5 plus 8. So the top of the fraction would be 30.5. Square root of 254 times 2. The bottom of the fraction is messy, but if I do 30.5 divided by that full answer, then round to the 100th. So I just got 0.956. That would round to 0.96. 956, so that bumps up to 96. Okay, now do the same thing for revenue. For part B, here's the revenue function. Revenue, 896, x minus 4 squared. Plus 29r squared. Equals 24,389. And we're still working with x equals 4. But we're probably going to have to plug 4 in here. Oh, that's helpful, actually. Plug 4 in here to get what the r equals, because in our derivative, we're going to have r in the derivative. Luckily, they gave us 4 here because 4 minus 4 is 0. 0 squared is 0 times this is 0. So it would have shortened to this right here, actually. So 24,389 divided by that 29 here. And then that would be r squared. So take the square root. Does it come out evenly? Yeah, it comes out exactly to 29. So that's better than the other problem. That came out exactly. So when they don't give you both of the variables, sometimes they just give you x. You have to plug it into the original problem and solve for the other variable that way. So now the derivative of revenue with respect to x Anytime I get to an x part, I'll just do the derivative normally, but if I get to an r part, then I got to attach a dr over dx to it. So this part right here would be a chain rule, because there's a parenthesis right here. 2 times 896, 1792, times the base, decrease the exponent by 1, and then the derivative of the inside, luckily that's just 1 though. And that's an x variable, so nothing to attach to it. The derivative of this would be 58 for 29 times 2. R to the 2 minus 1 is 1, but then I need to attach a dr over dx of that. And then the derivative of that is nothing. So I don't know if we need to distribute that, so let's just subtract this all the way over here on its own. 58r times dr over dx would equal negative 1792 times x minus 4. And then I can divide by 58r. Here's the derivative function if they wanted the answer to it as is, but we're going to plug in both 4 and 29 here. So put a 29 there and put a 4 right here. Although 4 minus 4 is 0, the top is 0, the bottom's not 0, but 0 divided by anything that's not 0 is 0. So that's weird. Marginal revenue is 0. Okay. So marginal revenue means how is revenue changing at the instantaneous moment in time. So apparently your revenue is not changing. You're bringing in the same amount of money as before. A business wants to know about marginal revenue being positive. That means you're bringing in more money than you used to. That means whatever you're doing is working. But if marginal revenue is 0, then you're just staying constantly. Your revenue is staying constant, basically. Okay, so that's it. 10 out of 10. I didn't know if there was another part to that. We got all 10 problems done now. So we're moving along here, and we're in a 3-week block of time. This is the end of the second week of the 3 weeks. So where am I here? Right here. So last week we were supposed to do 5-1, 5-2, 5-3. I had 3 videos out for those 3. This week we needed 3 videos, 5-4, 6-1, and 6-4. So next week is the next testing week. At the end of next week, November 11th is when the test is due. So, whoops. So next week there'll be 2 videos instead of 3. The first half of the week you'll be working on 6-5, and then the second half of the week, the review. And then all 7 of these sections plus the review and the test are due November 11th, Friday, November 11th, 11:59 p.m. The test itself, test 3, has already been created, but it doesn't appear until November 10th. It'll pop in here on November 10th when you're first able to take it. So you can take the test either next Thursday or next Friday, your choice. Then the week after that, there'll be the week after the test is the last full week before Thanksgiving break. So there'll need to be 3 videos that week too. We'll do a 6-6, 7-1, and 7-2 that week. Actually, I think what it is that I think on the calendar it says 6-6 and 7-1 for that week. And then the Thanksgiving week is officially Monday and Tuesday only, so I put 7-2 then. But I might make all 3 of these that week and just get them out to you sooner. And then I won't be bothering you during the Thanksgiving week that much. And at least you won't have to do anything over Thanksgiving. So when we come back from Thanksgiving, then we'll have 2 more weeks before the final week. So then you'll do 7-3 and 7-4, just 2 videos the week after Thanksgiving. And then the week after that's the usual where you do 1 section the first half of the week and review the second half. And then test 4 will be due December 9th. And right at that moment in time, then there will be just 1 week to go where all we're going to do is review and take a final. So officially, there'll be another 4-week block after we take our test next week, there'll be 4 weeks to do all this stuff. But one of those 4 weeks is a Thanksgiving week, and we don't have anything scheduled on the Wednesday, Thursday, or Friday of that week. This 7-2 is officially scheduled for Monday and Tuesday of that week, but I might do it early and let you, if you want to get it out of the way and not have to do anything for Thanksgiving week, that's fine. So I just wanted to work this out in my own mind where we're at this point. So for now, we're only worried about next week. We just have one new section and one review. That's what we're going to have next week. So see you next week for section 6.5 and the review.